Okay, good afternoon. I start with the usual question about possible doubts that you have, curiosities, questions on what we have done. And I also remind you that every time you have to work on what we have done, try to repeat the algebra, make sure you fully dominate what we have seen, okay? Don't lose contact with what we do. So don't wait until the final to really prepare your abilities, okay? Okay, so I summarize what we showed last time. We showed that in order to describe a wave packet, a possible solution of this problem is to write something like this. Okay. Where, in order for this to describe really something moving like a non-relativistic particle, omega k should be h bar k squared over twice the mass, okay? This was a necessary condition in order for the group velocity of that object, that was the derivative of omega k with respect to k, calculated at the mean k vector k0, where this was center, was just equal to h bar k0 over m, or if you want, the momentum over the mass, okay? And we also saw the big impact, numerical impact of having h bar of that amount, and especially of having m, if you have an electron, very, very small, okay? That makes quantum effects very important, because we noticed that one of the quantum effects was the beta, the second derivative of omega k, which in this case is just 1/2 h bar over m, and this beta being relatively large if the mass is the mass of the electron, while being very, very small if the mass is, say, the mass of a microscopic object, but still, not atomically small. Okay? So we saw that this described a wave packet, something localized, depending on the property of the g of k. It could be more or less localized, okay? And moving with a certain group velocity and spreading inevitably due to the fact that beta is different from 0. What we did last time was specifically for a g of k that was a Gaussian centered on a certain wave vector k0. To be honest, everything actually can be written in pretty much generality, okay? So you can assume that expression to be the expression of a generic wave packet, okay? A superposition of plane waves, okay, with the usual time dependence given by this non-relativistic expression, and this g of k could be any weight function as long as normalized appropriately, okay? Even more, you do not necessarily have to limit yourself to 1D, to one dimension, okay? You could think of this to be three-dimensional position and three-dimensional k vectors. Obviously, wherever you have kx, you should have in principle, so this become three-dimensional integrations, this become to the cube, and this is g of k, and this becomes k dot x, okay? So the k vector is a three-dimensional vector, and x is also a three-dimensional vector, okay? This is a three-dimensional wave packet. Remind you, for a free particle, there is no potential here whatsoever. It's a particle moving in vacuum, but non-relativistic. The analog of this, obviously, is k squared, okay? So kx squared plus ky squared, to be explicit, okay? Kz squared. okay, over 2n, or k dot k, whatever. Okay, so you can do this even in 3D. Now let me show for you the first interesting thing, which has to do with Schrödinger, and is the fact that these are indeed the most general solution for the free particle Schrödinger equation. Question?
Okay, we were saying that for the wave packet, each wave was propagating with the velocity v, g, the group velocity. Okay?
Mm-hmm.
And what if the wave was centered at the origin, the Gaussian?
Okay, the question is, what about if the Gaussian is centered at origin, okay? Which means that there is 0 group velocity, okay?
The wave cannot propagate.
I mean, the thing doesn't move, stays there and spreads. 0 momentum, 0 velocity, the wave is centered in the origin and just broadens, doesn't move. It describes a particle that is classically standing still. No momentum, no velocity, no nothing, okay? Particles can stay. Quantum mechanically, obviously, they have a width, and in fact, this width increases, okay, due to beta. If you have a classical particle with 0 momentum, the particle stays wherever you put it, okay, say the origin, okay?
But it's always possible to define K0 to be the center of the Fresnel frame.
But once you fix a certain frame, then you have to tell me if K0 is 0 or not. I mean, what you mean is, what about Galilean invariance? I mean, if I have a K0 different from 0, if I put myself in the frame where that is 0? Maybe we should discuss more this thing later on. For the time being, I mean, all I have done holds true even if K0 in principle is 0. Okay? Simply, the group velocity of this wave is 0, which means that the wave doesn't move as a whole. Obviously, the individual components of the wave move. The phase velocity of each wave, for k different from 0, is moving. But the overall thing is just a broadening of the wave and not a shift of the wave. Okay? But we can discuss more the details, but hopefully this is at least clear to everybody. Okay, so I want to prove for you the following thing. I want to prove that this object, this wave packet, is a solution of this equation. I will explain to you the symbols in a second. Okay, h bar we already know. I, well, is the usual complex thing. This is the first order derivative in time, okay? This object here, apart from the minus, the h bar square, and the 2m, is an object which we will repeatedly encounter, is the so-called Laplacian. I'm doing things here now in 3 dimensions. So in 3 dimensions, this object is the second derivative with respect to x, plus the second derivative with respect to y, plus the second derivative with respect to z. Okay? If I was working again in 1D, obviously I would have simply second derivative with respect to x. Okay? So it's the sum of the 3 second derivatives on the, say, 3 direction. This is the Laplacian. Okay? Okay. How can we verify this statement? Well, just direct verification. But in fact, I don't even need to substitute integral blah, 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 because you see this is a linear equation, right? Psi appears linearly. There are only these operators, the derivatives appearing, but psi is linear. So if I can verify that this is true for every single wave of this type, let's call this object psi of k, x and t, okay? It's a pure plane wave of momentum k. If I can verify that this thing is true for psi of k, then you probably agree with me, the same equation is totally verified by psi. You just multiply by g of k, integrate both sides, and since g of k and the integral do not interfere with the derivatives, you're done. Okay? Is this clear to everybody? Okay? So rather than writing these integrals in g of k, I am happy enough in verifying it for a single plane wave of that type. Okay? Let's do it. Left-hand side. The left-hand side involves a derivative over time. So I, h bar, the derivative over time. When I take a derivative over time, I bring down minus I omega k. Okay? So I have minus I omega k, and then I have exactly the same exponential. So e to the I k x minus omega k t. Is this clear to everybody? This is the left-hand side, the derivative with respect to time. Let us try now the derivative on the right-hand side. So I'm minus I h bar over 2m. And then I have second derivative with respect to x, y, and z. So let's consider the x. When I take the first derivative with respect to x, remember here I have e to the I kx x plus ky y plus kz z. Okay? This is what I have there. Okay? Now, when I take the first derivative with respect to x, I bring down I kx. Right? Okay. I kx. Then I take a second derivative of the same expression, and I bring down another I kx. Okay? So I get the square. Okay? Times the same function. All right? Let's do the second derivative with respect to y. Similar result. Okay? So I get plus I ky squared. The third, same thing, I kz squared. Now, the square of the i's with a minus conspire to make a plus. And overall, this object here is just plus h bar square over 2m, the square components of the k. Okay? So k dot k. K squared, in other words. The scalar product of k with itself times the same object. Okay? Is it clear? Simple algebra. On the left-hand side, let's look at again. I have I and minus I, which is plus 1, because I and I is minus 1, but there is an extra minus. So this is h bar omega k times the same thing, e to the I. And you see that obviously the two left-hand side and right-hand side coincide, provided this is equal to this. Okay? Which is exactly the choice we justified last time. Okay? Omega k being quadratic in k. You see? It's exactly the same thing. If you put here an h bar, this becomes h bar squared. Okay? And it is the same object. Clear to everybody? Okay. So with the non-relativistic dispersion for omega k, that wave, this plane, single plane wave, satisfies this equation that, by the way, is called the Schrödinger equation for a particle in vacuum, I mean no potential. Okay? And obviously, since a single plane wave verifies it, also a wave packet of this type verifies it. Okay? So I can eliminate, if you want, this and state in full generality that the wave packet satisfies it. Is this clear? Okay. Later on, we'll do some problems like scattering by a step potential, for instance, and we will study that, for instance, a plane wave impinging on a step potential is partially reflected and partially transmitted. We will do this thing in detail. Now, you realize that in principle, you have now a tool to study what happens to the wave packet impinging on the potential. Because all you have to do is to study each single plane wave. Each single plane wave is reflected with a certain reflection coefficient R of k and transmitted with the coefficient T of k. And the full wave packet is a superposition of all, okay? So a piece of the wave packet with the reflection coefficient is reflected back, and the piece of the wave packet is transmitted forward, okay? So in principle, although it requires not only studying the reflection and transmission of a single k, but also integrating those things on k, in principle, you have a tool to study what happens to an actual wave packet being scattered by a step, for instance. Okay? Just to give you an idea of what type of things you can think of doing. Okay. Question? Okay, let us try to study a little bit more the basic things behind. First of all, consider the following object. The operator minus I, h bar, the gradient, okay? Here I have the Laplacian. So the square of the sum of the second derivative. What is the gradient? The gradient is an operator that has three components, okay? Minus I h bar. First component is the derivative with respect to x. Second component, derivative with respect to y. And third is the derivative with respect to z, okay? So it's a vector operator. Okay, now, what happens if I apply this object, this differential operator, to the plane wave? So let us study minus I h bar, the gradient, applied to the psi of k that I indicated there. It's very simple. There is a minus I h bar in front, and then the component x involves a derivative with respect to x, which brings down, as we said before, I kx. And obviously, the wave is, remains there, because the derivative of the exponential has the exponential. Okay, the second component is I ky, and the third component is I kz. So all in all, if you collect everything, you will see that you have h bar kx, h bar ky, h bar kz times the same wave. Okay? So probably this is something, whenever you have an operator, call it A, and the vector is such that the application of the operator to the vector brings some number times the vector, then you say that this object is an eigenvector of the operator, right? This is linear algebra type of concept. So this is an eigenvector of A with eigenvalue lambda. Now this is telling us, therefore, the following thing. The plane wave of momentum k is an eigenvector of this momentum operator, which is a vector, with eigenvalues. Well, the first component is h bar kx, the second component h bar ky, and the third component of the operator h bar kz. Okay? Or, just to be short, h bar k times psi of k. Okay? So this is the operator. This is the vector, the eigenvector, psi of k, and this is the eigenvalue. All right? So this operator here, minus I h bar the gradient, has the plane waves as eigenvectors with eigenvalues, just notice the numbers, these are numbers, h bar k. 3 of them, but still a vector of numbers, which are the wave vector k's. Okay? So it is very natural, since we said that h bar k is a momentum, to call this the momentum operator. Okay? So for us, from now on, the momentum operator is just a 3-component vector, which is minus I h bar the gradient. All right? Very good. And the eigenfunctions of the momentum operator are the plane waves with eigenvector, with eigenvalue h bar k. Well, one more thing. Let's see, the Laplacian. Let's revisit the Laplacian. Consider the momentum operator dotted into the momentum operator. This means simply px plus py plus pz. What does it mean? It means act with px and then with px again. Another way of writing it is obviously px squared, okay? Plus py squared plus pz squared, okay? So this is the dotted product of the operator p with itself. Is just the square of the 3 components. Hopefully it is clear what is the square of an operator. It means acting twice. You apply and you apply it again. Now, it's pretty clear that applying the operator one time means taking minus I h bar, the derivative with respect to x. Applying it one more time means applying one more derivative, okay? So this object here is minus I h bar squared times a second derivative, okay? It's the application 2 times of a derivative operator. And minus I squared is simply minus h bar squared, okay? Therefore, all in all, this object here, you can rewrite also as minus h bar squared, second derivative with respect to x, plus second derivative with respect to y, plus second derivative with respect to z. Okay? So you see, it's just the Laplacian, apart from this coefficient, minus I h bar squared. All right. Therefore, you see that what appears here on the right-hand side of this Schrödinger equation is what? I can equivalently rewrite this as p operator squared divided by twice the mass, which is classically very understandable. It's the kinetic energy, okay? So the momentum operator squared divided by twice the mass is exactly what was written here, just in this squeeze. Okay? Very good. So if there are no questions, I'm happy with this very preliminary thing. So once again, I didn't really prove for you this Schrödinger equation. I just constructed a wave packet which, with some argument of reasonable describing a classical behavior, I said, okay, then this dispersion should be like that. And it happens that this is indeed a solution of the Schrödinger equation. Now, let's be a bit more general. And now I do not pretend to really prove for you anything. If the particle is not free, so if together with kinetic energy there is also a potential energy, Schrödinger tells us the following thing. that I should solve this equation. Let me just make the thing cleaner. Plus v of x times psi of x and t. Okay? It's exactly the same part, the same kinetic part, but on top of that there is also a potential piece. Okay? This is the full Schrödinger equation for a particle in a potential v of x. The object here, okay, is a very important operator, is the kinetic part. You see p square. Sometimes I will omit the vector notation, the thing, or maybe I will put just the vector like that. You always have to intend that these are operators whenever I discuss in a quantum mechanical context. Okay, so this is the kinetic energy plus the potential energy, and therefore you know that this is the operator that strictly corresponds to the classical Hamiltonian. It's just in quantum version, where this is an operator of Laplacian type. Okay? So another possible way of writing this is that this is the Hamiltonian applied to psi of x and t. Notice the Hamiltonian acting on a function is not simply multiplication by something. The potential is simply a multiplication by some obvious function, but this is taking derivatives, so it's a pretty much, in general, complicated object. Okay? Clear? Okay, so this is the Schrödinger equation we will study in this course. Now, you start seeing that the actors of this field are functions and operators. Okay? Psi is a function, and p square, v, everything else you have seen is an operator acting on functions, which could be a simple action like multiply the function by some other function, or a more complicated action like taking a derivative or taking a sum of second derivatives. Okay? Operators and functions are the actors. So until now we have seen p. X is also an operator, a simple one. X applied to a wave function simply means multiply by, depending, x component, y component, or z component. Okay? P acting on a wave function means taking derivatives. H means this complicated combination of things. Okay, some comments about this equation. First of all, you see there is a very, very strong asymmetry between space and time. There are second-order derivatives in time, but only in space, but only first-order derivatives in time. Okay. The fact that this first-order derivative in time implies that in order to find the solution of this equation, how many initial data you have to give me. Okay? Let me rephrase first in a classical context. If I have to study the Newton's equation for, say, a particle in a force field or 3 particles, whatever, what initial conditions do I have to give? Position and velocities of all the particles at the initial time. Okay? The Newton's equations are, in fact, second order in time. Sorry. Let me erase a few things here. You can write them as follows. Okay? Multidimensional in general, second order derivative here, and you need therefore to tell me what x at time 0 and what x dot at time 0 are. 2 information, or 2 vectors of information. at the same time, you can reduce this to a first order problem in the usual way. You just define x, the derivative with respect to time of x, being the momenta. And obviously, this is telling me that the derivative of the momenta with respect to time is equal to the force. So in this form, you see it's a system of first order differential equation. And again, the information you have to give him is the same. Initial position and initial momenta, or velocity. Okay? So for each degree of freedom appearing in first order, you have to specify the initial condition. And this is pretty simple. After all, an equation of this type, if you have to study it on a computer, how would you discretize it? Suppose that, let's simplify things. Suppose that you are in one dimension and you have just this. How would you study it? Well, you would say x at time t plus a certain delta minus x at time t divided by delta, that is my estimate for the derivative, is equal to p at a certain time t over m. Okay? Therefore, if I know x at time t and p at time t, I can advance one step and calculate what is x at time t plus delta. Okay? It is simply equal to, well, x at time t plus delta over mp. All right? Okay? So you see, it is pretty obvious on a computer that first order derivative in time allow you to advance by one step by just knowing the initial value of the object, okay? And repeatedly applying this scheme, okay? Good. Now that I have here a first order problem, but for a function, okay? So you should imagine that you have infinitely many position x, and I should in principle specify the value at time 0 of these infinitely many positions, okay? So it's like having infinitely many particles in Newtonian mechanics, okay? So not one information, but a function, okay? So the full problem is specified once you tell me that at time t equals 0, the function is something, okay? And in order to specify that this is any function, but at a given time, I write it like this, okay? So this is called the initial value Schrödinger problem, time-dependent Schrödinger, okay? By the way, in principle, nothing forces me to have this Hamiltonian that, as you see, contains no time, okay? In principle, you could think that your potential, for instance, is due to some electric fields and magnetic fields and whatever, okay, external objects that depend on time, okay? So in principle, there might be a time explicitly appearing there. Or, even more, there could be a magnetic field by which you know that p square changes and the vector potential appears, okay? So there is really nothing special about this Hamiltonian being time independent at this stage. There might be time dependence, all right? So h might depend on t. But this doesn't change what I'm saying. So the problem is fully specified once you give me the initial wave function at some arbitrary time, say t equals 0, okay? This. And then I can, in principle, propagate this information and solve and find psi of x and t at any later time. I'm saying in principle. It's not an easy task, okay? You can imagine if studying the motion of, say, the planets, okay, in our solar system, it's a set of complicated enough differential equations. Well, this is a partial differential, how is called, a differential equation for partial derivatives, not ordinary differential equation. You have say here, second derivatives over x, y, and z. So it's a complicated problem, but in principle, first order in time. And therefore, once you give me this, I can integrate it. A question? Clear? Okay. Now I'll show you how to formally solve the problem. At least I'll do the simple case where the time is not there. In principle, even the case of a time-dependent thing can be formally written down, but it's very complicated and really not of much practical use, except for doing perturbation theory in a fancy way. Okay? So I will stick for the time being to a time-independent Hamiltonian. Okay. And what I want to introduce to you now is, oh, by the way, this solution is perfectly deterministic, okay? Pretty much in the same spirit as Newtonian mechanics. You give me the initial velocity and positions, and I can find exactly the velocity and positions at all later times. You give me this, and I can find exactly the function at x and t at later t. Deterministic. There is nothing probabilistic in here. The probabilistic aspects of quantum mechanics will come in a while, okay? And it is in the interpretation that I give to psi. I interpret psi as being the amplitude of probability to find the particle at a certain point. So the probability is psi of x modulo square. That is the probabilistic aspect of it. But this is a deterministic equation. Okay. Having said all this, let's start with a few mathematical machineries. I will introduce the mathematics slowly, okay? So not the theory of all Hilbert space possible things, all of, I mean, in 1 or 2 lectures, because that would be really too much to digest. Probably have seen many of these things, but I will introduce slowly the concept whenever I need them, okay? So for the time being, we have seen Laplacian and things, but one important object that is useful is the exponential of an operator, okay? So you know ordinary exponentials. They are known by the Taylor expansion, okay? So if I have now, instead of e to the x, e to the an operator O, how do I define it? Well, by the Taylor expansion. So this is 1 plus the operator plus 1 over 2 factorial the operator square plus 1 over 3 factorial the operator cube. The same Taylor expansion, obviously, of e to the x. Okay, this is a trick that is often used. Whenever you don't know really how to define things for operators, use the Taylor expansion, and you can define any function of the operator by the Taylor expansion. Okay? Operator square, operator cube are pretty obvious things. You apply twice, you apply 3 times in a row, as we have done for the momentum square before. Okay, so this is the definition. Right. Well, in short, sometimes you can also write it as sum over n from 0 to infinity of 1 over n factorial O to the n, okay? Interpreting, obviously, n equals 0 factorial as 1, as usual done, and also O to the 0 as 1. By the way, 1, what is it 1? As an operator, is the identity, means do nothing, just apply to a function, remains the function, okay? Okay. Now, one thing that you should be aware of is that the exponential of operators are pretty delicate. For instance, while if you have 2 normal exponential, e to the x1 times e to the x2, you know you can collect this. That's not true for operators, okay? While the 2 objects here, classically, they commute, so that doesn't matter the order. For operators, usually the order matters, and therefore you can convince yourself pretty easily that exponential of an operator O1 and the exponential of another operator O2 in general should be different from the exponential of O1 plus O2. Okay? This is not true in general. However, you probably know that if I have e to the alpha t, okay, and I want a derivative with respect to t, then I have just alpha in front. This is true for ordinary exponentials, for functions. And luckily enough, this is still true even there. So if I have the derivative with respect to time of the exponential of operator O times t, this is just the time times t, then this is still equal to O e to the OT. Okay? Like the usual thing. So bring down the operator. How do we prove this? I raised the Schrödinger equation for a while. By the way, it doesn't matter if I put the O in front or after, okay? Why? Because after all, this exponential of the operator O contains only O and powers of O, okay? And let me introduce immediately one other useful concept. The commutator of two operators, okay, is simply measures the difference between acting in one order minus the opposite order, okay? So for numbers, this would be 0, because it doesn't matter the order in which you multiply. But for operators, that's not true. It matters if you first take a derivative and then multiply by x, or vice versa. You first multiply by x and then take the derivative, okay? It matters. Now, O obviously commutes with any power of itself. So if I take the commutator of O with the square, I should just obtain 0. Why? Very simple, because one is just O square, which is O cube, minus O square O, which is O cube. So O cube minus O cube, 0. Okay? So O commutes with any power of itself. And obviously it commutes also with the exponential of itself, because after all, the exponential is nothing but a sum of powers. And obviously this commutes also if I put an extra constant t there. By the way, the extra constant simply plays a very simple role. Accompanies O everywhere, obviously with the appropriate power. Okay? Clear? Okay, so they commute, and therefore it doesn't matter if you write it before or after. Okay, let's prove this simple equation, and it's a direct proof. I take the derivative of this object here, okay, with respect to t, in the usual way. So for instance, if I take the derivative, let me write it here, derivative with respect to t of 1 plus OT plus 1 over 2 factorial O square t square plus 1 over 3 factorial O cube t cube. I stop here. Okay? Now, identity doesn't depend on t, and therefore the derivative completely drops. Okay? So 0. Plus, this is linear in t. I take the derivative, I get O. So I eliminate the 0. Plus t squared. The derivative is 2t, right? So the 2 cancels a piece of this and becomes 1 over 1 factorial, or 1, O squared t. Plus derivative of t cube is 3t squared. The 3 cancels a piece of this, and this remains 2 factorial. O remains cubed, and this becomes t squared. We'll try to imagine what happens afterwards. Okay? So you see that there is now a disparity between the t and the o's. The t are 1 power less. Nothing really dangerous, nothing really bad. Let's put a common o in front of everything, a common operator. Then the first one is just multiplying the identity, plus the second one is multiplying OT. Okay? You see that the factor in front is just 1. The second here is multiplying 1 over 2 factorial O square T square, plus you realize that this reconstructs exactly the exponential series you see here. Okay? Is this clear? Okay. So we have proved this. By the way, instead of putting it on the right, I might have just taken it from, on the left. I might have taken it from the right and just put it there. It's the same result. Okay. Very, very, very good. Now, you might ask, why do I invoke this objects, the exponential of an operator? Well, it's useful. Let's see. Take as operator O the following object. Minus I, the Hamiltonian operator, divided by h bar, times t, obviously. Okay? So this will be my O. Okay? What is that thing telling me is that the derivative of this with respect to time will bring down me the bubble here. So minus I h over h bar times the same object, the same exponential. Is this clear? It's just a simple application of the very general derivative I showed before. Okay? You still might be puzzled by why I invoke this. But now, let us look more closely to our Schrödinger equation, okay, which was I h bar, the derivative with respect to time of psi of x and t equal to h psi of x and t. I'm taking now a time-independent h, okay? And psi of x and t equals 0 was some psi 0 of x. This was our problem. Now, you realize that if I multiply here by an h bar and an I can rewrite this. Maybe I have little space, but I h bar, the derivative, is just I square, and there is an h bar, and therefore this is simply 1. Okay? So this is simply h times the same object. This is already suggestive. I h bar, the derivative of this object, is equal to h, the object. The object is an operator. It's in fact a complicated operator. Not only h appears. H is already Laplacian plus v. H square appears. H cube, h to the fourth, all powers. And you can imagine how messy it is. For instance, h square, by the way. H square means Laplacian. Let me omit the h bar and the plus v twice. Laplacian plus v. And so therefore I have the Laplacian and Laplacian, so derivatives of order 4, but I also have Laplacian applied to v. So the Laplacian of the potential. I mean, it's a mess. And if you have 3 of them, you can imagine how many derivatives you have. So it's a complicated beast, okay? But formally, it's very well mannered, okay? It lets you write it at least. Okay. All right. Now, let me show that at least formally, this solves our problem. By the way, this object here is so important that it's given a name. It is usually called evolution operator and is often called U of t. So U of t is e to the minus I Hamiltonian t over h bar. By the way, when t is equal to 0, this is the exponential of 0 times the Hamiltonian. Exponential of 0, you see, is just identity. Okay? So U of 0 is just the identity. All right? So the equation that I have there is that, let me rewrite it a little bit cleaner, is that the derivative I h bar, the derivative with respect to time of the evolution operator, this exponential here, is equal to the Hamiltonian times the evolution operator. Okay? This is what I just showed you before. All right. Now, solution of that problem. I want to prove for you that if I take psi of x and t equal to the following object, evolution operator applied to psi 0 of x, okay? This was the initial function I give you, initial data, okay? Apply to it the evolution operator, and magic, there comes the exact solution. How can you prove that? First of all, let's verify the initial value constraint. Well, for t equals 0, the u of 0 is the identity, and obviously you get what you want. So all I have to really prove for you is that if I define psi in this way, and I take the derivative with respect to time, I get exactly the same thing as the right-hand side, okay? So let's do it. So I take this ansatz, and I to I h bar, the derivative with respect to time of u of t psi 0 of x. Well, but I know how much it is, right? This is simply equal to hu, this object, okay? So this is equal to h u psi 0 of x, okay? But u psi 0 of x, according to my ansatz, is just psi of x and t. So this is also equal to h psi of x and t, which is indeed the Schrödinger equation on the here. Okay? All right? So this is a magical object. It provides the, in principle, formal solution of your time-dependent Schrödinger equation. You just have to take the exponential of the Hamiltonian multiplied by t by minus h and divide by h bar. Now, just take that is an understatement. It's a very complicated object to construct in general, okay? So it's formally very nice, very simple to prove, but practically very difficult to construct. Otherwise, it would be very simple to solve this equation, which is not. All right. Questions until now? No. Okay. We have discussed so far about wave functions, operators, evolution operators, and things like this. But now comes the question. Remember our initial presentation where the electrons on the screen, the double slit experiments, the electrons coming one by one, tick, 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 hitting the screen. And after many of them, 6,000 of them, you would see a nice interference pattern, okay, with more electrons prevalently in some areas and less electrons in others. We have to ask the question, what does it mean to, how do I define the probability of finding an electron in some position x, okay? So the question I'm asking is, how should I, maybe I just erase this. the probability of having an electron, a particle somewhere in x at time t, how much it is? I mean, I have discussed about psi, but what is p, the probability? Obviously, it must be a probability, so something real, something positive. Psi, as you have seen, there are i's everywhere. And if you remember our wave packet, there was e to the I, kx, blah, blah, blah. If you plot it as oscillating, it's a real wave with positive and negative things, a real and an imaginary part. So obviously, psi cannot be the probability. So this is not psi. Well, one might say, okay, psi is complex, take the absolute value, okay? This is real, it's positive. Well, doesn't work. There is a very unique, almost unique choice that you can make for this P. And because I want to satisfy a few very important constraints. Let's see the constraints, and then I tell you what is the solution. The constraints are P of x and t should be real and positive. Constraint A. B. Things do not disappear. Okay? So the total probability of finding the particle somewhere should not change in time. Right? So this thing should be 0. Okay? This is the total probability and should just be constant because particles are neither created nor disappearing. They're there. Obviously, since this is a constant in time, I can, and since in some sense the equation is linear, the Schrödinger equation, I can always rescale everything by a constant. So therefore, if you want, I can always impose something even more stringent, that is that the integral is just 1. This is indeed what the probability should do. Okay? So obviously, if this is true for any time, then the derivative is 0. But this is just a choice. So total probability is conserved in time and is a positive, at least non-negative real quantity. This is a non-negative real quantity, but if you use this, the total probability would not be conserved. And anything else but this doesn't work. Okay? So the only thing that works is the square modulus of psi, and then the total probability is conserved. Okay? So this is what we want to show next. This reminds you a little bit about electromagnetic energies, okay, being related to the square of the electric field, the magnetic field, okay, the energy of the thing. And notice also that this fact already embodies a very curious characteristic of quantum mechanics. At the level of the Schrödinger equation, looks like a wave equation, and you can superimpose waves. So you can have, for instance, a wave psi 1 and a wave psi 2. And if both solve the Schrödinger equation, I can sum them, and even the sum solves the Schrödinger equation. However, if I ask myself about the probability of finding the particle now in this new wave that is the sum of the two waves, I have to take the square modulus of the sum, which is different from the sum of the square moduli. Okay? So the square modulus of the sum is just equal to the square modulus of psi 1 plus the square modulus of psi 2 plus a term that comes from psi 1, psi 2 star plus psi 1 star, psi 2. Okay? So things of this kind. Now, this is the probability in the first wave. This is the probability in the second wave. This is the probability in the total wave, which is different from the sum of the two probabilities. Okay? You might say, okay, waves do this, in fact. Okay? I mean, interference is just in these terms. So whenever you have wave phenomena, this is always there. So be careful to the fact that this object here already embodies interference in a very natural way. Okay. Now, to prove this, to prove that with this choice, in particular, well, A is obvious. The only tricky thing is to show B, in fact. Okay? Once you have B, obviously, you can just normalize the psi and impose this one. Now, I could proceed directly. Okay? I have the form of P, psi modulo square. Here there's a derivative. I know what derivative of psi do, because I know the Schrödinger equation, and I could do the calculations and show that it is 0. However, this would be a brutal exercise in some sense. I want to show you a few more mathematical tools that are useful in general, and therefore it's good to introduce them now and apply them right there. Okay? And the tools are the following. First of all, the space of those functions, psi, okay? You realize that I can sum two functions, and therefore, and I can multiply a function by a constant, therefore they form a vector space, right? This vector space, I will call it H often, okay? H kind of tilted, not to be confused with the Hamiltonian. Will be in a second Hilbert space. They're called Hilbert space. It is Hilbert space only after I introduce a distance in this space, in particular a norm, how to measure lengths of vectors. Okay? Like in three-dimensional space, you have the space of vectors. You can introduce the length, for instance, the Euclidean length of a vector, sum of the square components of the or components. Okay? So, for instance, in the 3D case, R3, you have a vector, and you have the, well, let's do, you have a scalar product, in fact, V1 scalar product V2 is equal to, or sometimes indicated like that, same thing. This is equal to component X plus component Y plus component Z, okay? So how do I introduce a similar object for my space of function? Now, there are no longer a finite number of components. They are functions, so there is an infinite number of components. You might say, okay, what is the problem? Rather than a sum over a discrete index, I have an integral. So if I have two functions, psi1 and psi2, the scalar product, and now is usually really indicated like that, I just take the integral rather than the sum over all space points, and then I take psi1 of x times psi2 of x. Just normal multiplication. Almost right. Since these are complex objects, the thing to do is to put a star there. The reason is simple. I mean, if I take the scalar product of something with itself, psi1, psi1, if I don't take the star there, I have psi1 squared. But psi1 might be a complex function, and so this object might be complex, whatever, okay? And that's not nice. For vector, it's obvious. The square is a real number, and that is the length, the Euclidean length. In this case, if I put the star, this becomes the integral over x of psi1 x modulo square, which is real and positive, and therefore it's reasonable to call this the length of the function, the norm of the function. In fact, it's a very well-known norm. It is called the L2 norm. There are many ways of defining what is the length of a function, and this is one. All right. This is in fact called the norm of the psi1, obviously modulo square. Okay? So if I want the norm, exactly like for the Euclidean case, you have a square root of the sum of the square, or the integral of the square. Okay. In the same spirit, you have a scalar product, and that is the thing. Okay? Now, to be honest, you have to specify that H is a space of all psi with the usual rules of the linear spaces, and such that psi is finite. Okay? So they are normalizable. This is a very reasonable thing. After all, the integral of this object here is the integral of, in retrospective, from what we are going to show in a while, this is the probability of finding the particle in this function psi1, and obviously you want to have things that are finite objects. As a matter of fact, we will often discuss plane waves, for instance, which are a very natural object, very simple to work with. We have already introduced, in fact. But if you think of it, the plane waves do not have this property. If you take the integral of the square of the plane wave, since the square of the plane wave is 1, this integral is just infinite. Okay? So you see, the plane waves, strictly speaking, do not belong to the set of normalizable states, which is a bit unfortunate in some sense, because they are so useful. Nevertheless, they are very useful, because with them, remember, I formed my plane waves, my wave packet, by just superimposing many plane waves. Let's forget about the time, okay? Just a fixed time, okay? So the plane wave by itself is not normalizable. But if you superimpose many of them with the appropriate weight, you can form a perfectly well-defined wave packet which oscillates and decays very soon, which is normalizable, okay? So this thing could be very well normalizable, while the basis object here by itself is not. That is a reason why you keep using them, although you always have to realize that when you want to define things very precisely, alone they are not physical. Only when you form wave packets they become kind of physical. Okay? Is this clear? Okay. In some sense, they are basis vectors. Each one of them is slightly unphysical in having an infinite integral, but with them you can express in this powerful Fourier transform way any function. Okay? Okay. Well, let us proceed. Where should I proceed? Here. We'll study a little bit more this fact about plane waves that are not normalizable, because especially in condensed matter, I would say, we work with a device that is called, is working with the system in a box, okay, of a finite volume, with certain boundary conditions on the limits of the box, which are called periodic boundary conditions. And then at the end of the calculation, you take the volume of the box to infinity. Now, for every finite volume, there is no problem. The plane waves are very well defined because the volume is finite. Okay? You do all your calculation, and at the end, you take the limit. This is a possible way to make things, in some sense, well defined, even with the plane waves. And is very often used in condensed matter. We will devote kind of 15 minutes to this idea, because I think it's very useful in calculations. Okay, especially if you go over to condensed matter next year. What should I tell you? Yes, still a bit of mathematical apparatus. So Hilbert space, the scalar product, the length, the norm of a function. Operators. We have seen already some operators. I define for you now a very important class of operators. They are called Hermitian operators. Hermitian operators. How are we with time? Well, 15 minutes more. An Hermitian operator has the following property. This is the defining property. If you apply it to some wave function psi2, and then you take the scalar product with another wave function psi1, there is... Yeah.
I want to ask, you said something about, I did not get you about this, the last one. Yes. What did you say? To normalize.
He is asking what is behind my discussion here about this being normalizable while this is not normalizable. Okay? Now, what I was saying is this. If you are working in infinite volume, let's do it in 1D, okay? If you are working in the infinite line, this object here is not normalizable in the sense that the integral over dx of the modulo square of e to the ikx, which is 1, is simply infinity. Okay? On the contrary, if you take this and multiply by some weight function, for instance, let's take our Gaussian. Okay? You remember what the result was. The result was, if this was constant e to the minus alpha k minus k0 square, you remember that the result was something like constant e to the minus x square divided by 4 alpha times other things. Okay? But this is a very nice object. Very smoothly going to infinity quite fast. Well, it depends on alpha, but for any alpha, you can integrate it. Okay? And therefore, there's no problem. And in fact, with the normalization I was choosing last time, check. I was normalizing things with the c constant, blah, blah, blah. You can verify the integral was exactly 1. Okay? So the normalization was such that the norm square of psi of x was 1. Remember I was discussing we have to normalize things in such a way that the square, the reason for the square is this, because we introduce things in this way, not just, okay? These are normalizable, although the individual pieces that you sum together and do this integral are not. Nothing strange, okay? Clear? All right, so let's go back to the in fact, let's erase this. So the operator is said to be Hermitian if, when acting on the right-hand side of the scalar product or acting on the left-hand side, it's exactly identical. Doesn't make any difference. In other words, the Hermitian operator can travel back and forth. Okay? They can act on the right or on the left, no difference. And I have to warn you that on the right there is psi2, on the left there is psi1 star. Okay? So let's start revisiting our operators encountered so far. For instance, x, multiplication by x. Let's do it a single component, say the x component, for instance. This is x. Psi2, psi1. What is it? Well, it's the integral over all space, 3 components, in principle, of psi1 star x multiplied by x psi 2. But x is real, and therefore I can identically write this as x psi 1 x star psi 2, because x is equal to x star. Okay? But this is what? This is x acting on the left multiplied by psi 2. In other words, this is x psi 1 scalar product psi 2. Okay? So you see x being real is a free traveler, can go back and forth from the right, from the left, and vice versa. And obviously x squared, x cubed, any power. And you realize any potential with any arbitrary form, any Taylor expansion, whatever, a real function can travel back and forth. Okay, no problem. So all potential, the v of x, which are powers and whatever functions of the positions, are also Hermitian because they're real. Not a complex potential, by the way. Okay? So if the potential is an imaginary part, that is not an Hermitian operator. Okay. We'll never really encounter complex potential, although they have been introduced. That doesn't matter, okay? I wouldn't know how to tell you much more than that. Let's start looking now at momentum. Now, let's see. The momentum operator, P. Again, let's consider a single component, for instance, the x component. Now, what you have to do is to put minus I h bar, the derivative with respect to x. And you might be worried about this I. I doesn't look like something that travels easily into a star. But in fact, I will show to you that P is Hermitian just because of the I in front. Without that, it would not be Hermitian. Okay? And the reason for this is very clear. Now, when you have an integral with a function times the derivative of another function, you know that you can do integration by parts. Okay? So in a case like this, you would say, okay, I know how to integrate this, so there's a minus I h bar. The integral of this is psi 2, so I have psi 1 star psi 2 x evaluated between, say, plus infinity and minus infinity. Let's do it in 1D. Okay? All right? Then I have minus the same object. Now the derivatives appearing on the left-hand side. So I have here the derivative of psi 1 star psi 2. Okay? This is integration by parts. Now, these functions are normalizable. I am working on the assumption that these are states that are normalizable. Therefore, for very large x or negative large x, both functions should decay to 0. And therefore, this boundary piece is just 0. Let us now look at this object. This is certainly the derivative of psi 1 star or the derivative of psi 1 all star. But you see that here I have a plus I. Now, I can equivalently write this as the integral over dx of minus I h bar, the derivative of psi 1 all star psi 2. Let's verify. Well, the minus I with the star becomes plus I. And this is indeed the plus I. Okay? All right? So you see that it's crucial. The integration by parts commands a change of sign here. Okay? This is required by just elementary analysis. That in the integration by parts you have a change of sign. Well, thanks to this star, the change of sign is exactly cancelled if you have the I. Okay? And so you see that this is nothing but P psi 1, psi 2. Okay? So P was able to travel from the right to the left, thanks to the I. Without the I, not Hermitian. Okay? Now, let me, in the remaining few minutes, point out a few other properties of, if I have an Hermitian operator and I square it, obviously, I obtain still an Hermitian operator. This is pretty much general, okay? If the operator O is such that it can travel here, when I have the square, well, this is simply the operator O acting on the operator O psi 2. Okay, so let's do it a travel at a time. O is Hermitian, it can go here. But the resulting thing is equal to O psi 1, O psi 2. But O is Hermitian, as I said, and can travel here. And so you see you reconstruct O square on the left. Is it clear? So if O is Hermitian, O square is Hermitian. And a simple exercise shows you that any power is Hermitian. So any power of an Hermitian operator is still Hermitian. Okay? Very, very simple. Now, since you have proved that P is Hermitian, this will tell you that P square is Hermitian as well. And the sum also of two Hermitian operators is Hermitian. You can prove this in a few seconds, okay? So if I have an Hermitian operator O1 and then another Hermitian operator O2, the sum of them is also Hermitian. This is very simple. First of all, you break this scalar product into pieces by linearity. Oh, by the way, I've not been mathematically very sophisticated. I mean, I should have proved for you that this object here is bilinear. I mean, if I have here the sum of two things, then I get the sum of the two scalar products, right? Because I have two functions here, okay, which is simply, I mean, it's linear on the right and linear with the star on the left. Is this clear to everybody? Yes? No doubts? Okay, good. Now I'm going to use it. That's the reason why I stress this. You see, I have here the operator plus another operator applied to, so the sum of two functions. The scalar product of psi 1 with the sum of two functions is the sum of the two objects. Okay? But now each one of them is Hermitian, so I bring it here. And now I use again linearity on the left this time to recollect the two into a single object. Okay? Clear? Okay, so even the sum of two Hermitian operators is still Hermitian. It can travel. All in all, we have seen that x, v, and a real function is Hermitian, p square, sum of p squares, and therefore the Laplacian is an Hermitian operator. The Hamiltonian itself, because it's the sum of p square plus v, again, is an Hermitian operator. Okay? So all the operators, almost all of the operators encountered so far are Hermitian operators. I say almost because you could immediately tell me one that is not Hermitian, is the gradient without the I is not Hermitian. Well, trivial thing. Okay? All right. Now, why are these Hermitian operators so useful? I think I can take a couple of minutes to use this machinery, otherwise you feel that we have wasted time, to show what we wanted to show in a very few steps. Okay, so let's do it, although we will probably need 2 extra minutes. So the final statement is that the Hamiltonian operator, in particular, is Hermitian. Okay, so I have P that is equal to psi star times psi, because it's the modulus square. So when I take the derivative of P, I will have to take derivative of this term and of that term. Okay? Now, I certainly know that IH bar, the derivative, it's often written as a partial derivative because when I have psi, really, I mean, it's a partial derivative. Okay, like that is equal to H psi. Okay? Well, but then you know also what happens to psi star. Just take the star of this thing, and I have that minus I H bar. The derivative with respect to t of psi star is equal to H psi star. All right? Simple, right? Okay, so let's do now. Let us do now the calculation. So I have, in fact, let me put an IH bar in front. It's free, right? IH bar, the derivative with respect to time of the integral in dx of psi star. Let me omit x and t, okay? You know that they are functions of x and t. Okay? I want to be a little bit faster. Okay, so this is the object there, P, integrated over x, taking derivative. I take the derivative of this, and I leave that untouched, or the derivative of that, and I leave that untouched. So there are two contributions. One is this, psi star I h bar, the derivative of psi, when I take the derivative on the right, plus integral in dx I h bar, the derivative of psi star times psi. Do you follow? Okay. Now this object here is h psi, according to my Schrödinger equation. Okay? And what is this then? Integral in dx of psi star h psi. Let us write fancy. Psi h psi. Right? Because this is just a scalar product. Okay. This object here is simply minus, this is minus h psi star psi. I copy from there. This is equal to minus h bar. And let's be fancy again. What is this? It's minus h psi, acting on the left, psi. But h is Hermitian. So h can actually travel back and forth. And you see here you have exactly the two appearance on the right and on the left. And they are exactly the same. So this is just 0. Okay? You see in one line, or almost, okay? I didn't have to do much effort. And knowing that h is Hermitian is enough to conclude immediately that that total probability is conserved. Okay? I hope you appreciate how, I mean, having digested a little bit of machinery and mission operators and things, you can prove things in a pretty easy way. And you also realize how important is that P is psi modulo square. You see, this is at the basis of the length of the vectors, the definitions of all these scalar products. Without that, this wouldn't work, okay? The psi itself, that wouldn't work. Psi to the fourth wouldn't work, okay? Anything that you can imagine that is real and positive, it wouldn't work, okay? This works. All right, so I think that this is enough for today, unless you have questions. and we will reconvene next week to continue. Okay? Bye-bye.